All right, let's do this. So it is always a little tough to be back from Thanksgiving break, but we got one more week of content to go. So you just gotta like jumpstart your brains for one more week here, all right? We're going to focus this week on carboxylic acid derivatives. Okay, so this is a class of compounds very similar to carboxylic acid, so actually that's going to be our first one here. All right, and as we go through, it might become more obvious why we lump these together here. Okay, but yes, the first is our actual carboxylic acid, right, where you have a hydroxyl group attached to that carbonyl carbon. Okay, and this is actually going to be the common feature of all of our carboxylic acid derivatives, is having some electronegative element bound to that carbonyl carbon, as opposed to just being another carbon with ketones or a hydrogen with aldehydes. There's some electronegative element there. Cool. All right, so we can put a very electronegative element there, like a halogen. All right, and then these are what are called acyl halides. In this case, more specifically, an acyl chloride. You also hear these called acid halides, but that's not how I learned them, so I'm going to call them acyl halides. Okay, another one that's a really popular starting point in the lab is when you replace that bond on that carbonyl carbon with just another carboxylate. And this is what's called an acid anhydride. If we put an oxygen on that carbonyl carbon, but instead of making it a hydroxyl group, it's got some carbons coming off of it. This is not an ether, but the one that everybody loves to mix up with an ether. An ester. Or we can add a nitrogen on there. And this would be what we call an amide. So not an amine with an N, but an amide with a D, and some people call these amides, and again, I just pick one and stick with it, so I'm going to call them amides. All right, and then the last one kind of looks a little bit differently than all of these, but we still lump it into the same category because chemically it behaves very similarly. And these are what are called nitriles. Nitriles do not have carbonyl groups, but they do have a carbon with this really high order bond to a more electronegative element, this carbon-nitrogen triple bond. So we're going to sort of talk about reactions as we go through here, but for right now, just to be able to recognize these functional groups, these are our carboxylic acid derivatives. All right, we have carboxylic acid. They're all going to share this feature of this electronegative element bound to that carbonyl carbon, except for the nitrile. I don't know, that's kind of the odd man out there. All right, but if we replace that with an halogen, that's an acyl halide. We can replace it with a carboxylate group, that's an acid anhydride. All right, if we have oxygen but with some carbons on the other side, that's an ester. And if we have a nitrogen in that position, that is an amide. Cool. So we're going to talk about nomenclature. All right, but we're going to go kind of quick here because what we're going to just do is introduce our new parent chain endings for each of these functional groups. There's two of them that we're going to have to talk a little bit more in depthly about, but for the most part, you're just swapping out suffixes at this point. All right? So step one, that parent chain will have a different suffix depending on which one of these functional group categories this falls into. Carboxylic acids. They have the suffix oic, and then a space, and the word acid. All right, so I think this is maybe the first time we've seen spaces in our name. I don't remember. Anyways, very rarely do we have spaces in our IUPAC names for our different functional groups. Carboxylic acids are an example of when we have a space. It's you tack on the ending oic and then the word acid. All right. Those acyl halides. Use the suffix oil, OYL, and then the name of the halide. So butanoyl chloride or butanoyl bromide. All right, and we'll do a bunch of examples here, but let's just sort of lay down these rules. Nitriles, they got really creative, and they put the word nitrile on the end. Okay, there's just one thing that we want to note about this here that we've seen before with our thiols, and that is that these start with a consonant, right? Nitrile, our suffix starts with a consonant. So remember, that means that we have to retain that E on the end. How the hell do you spell consonant? It starts with a non-vowel. Okay. Amides, they also got really creative, and they just use the ending amide. All right, and then lastly, our esters. Are going to have two parts to it. You're going to have some sort of an alkyl group plus the parent chain, and that has the ending O8. And we're not going to worry about our acid anhydrides. They're actually pretty easy if they're symmetric, and hugely pain in the butt if they're not. So we're just going to gloss over those. All right. So let's do a few of these first. The first three are kind of the most straightforward. So let's just see if, based on everything that we've done this semester, if you can't name these molecules for me. right, so this first one here, we have these 1, 2, 3, 4 carbons. So we're going to use that prefix, bute. And we got all single bonds, so this will be butanoic acid. Okay, now if I'm going to number my parent chain here, where's going to be carbon 1, on the left or the right? On the right-hand side here. And what you want to convince yourself of is there is no way to have a carboxylic acid without that functional group being located on the end of the molecule, right? You can't have those 3 bonds sitting in the middle, so they're always going to be on carbon 1. So since they're always on carbon 1, do I have to say it's 1 butanoic acid? No, it's just going to be implied. And that's going to be the same with all of our carboxylic acid derivatives. That first carbon, they have to be located on the end. They all have 3 bonds, so they have to be on the terminal end of the molecule. So they're always going to be located on carbon 1, and so we don't include it in the name. All right? So by that same logic here, if we have these 1, 2, 3, 4, 5, 6 carbons in this molecule here, this would be hexanoyl. All right? And then we want to specify the halogen. In this case, it's chlorine, and chlorine is going to be by far the most common. So this is a hexanoyl chloride. Okay, right? We have that new ending, that OYL ending, plus our halide. Okay. Now for this one, I am confident that everybody got 5 carbons in their parent chain. I'm less confident that we agree on what 5 carbons those are, all right? The same logic that we applied to all of our other carboxylic acid derivatives. This carbon right here must be carbon 1 in your molecule. All right, this is a very common error that people make, is they think of this whole thing as being a nitrile group sticking off of this molecule. The carbon in that nitrile group must be carbon 1 in your parent chain. So given that, everybody take a second, see if you can't name it now that I've told you the curveball there. And let's just kind of make special note here for our nitriles. That C that's triple bonded to that N. All right, this must be carbon 1. Okay, so my name here would be 2-methyl. I got 5 carbons in my parent chain, so pent, but I can't say pentan nitrile and run those 2 N's together. So again, we're going to retain the E at the end and make this pentane nitrile. All right, so for nitriles, must be carbon 1. All right, we're also going to make a note that we retain the E in our parent chain. Okay. esters. Esters have these two parts to them, right? Because you necessarily have this oxygen that has some amount of other carbons on the other side. We had a similar sort of situation with ethers, and with ethers we said that we were going to cut and see which half is bigger. We don't do that with esters. Esters, you always know what side is your parent chain. It might be bigger, it might be smaller, but it has to be the fragment that contains that carbonyl carbon. All right, so for esters, the parent chain must contain that carbonyl carbon. All right, so this right here, this chunk is my parent chain half of my molecule. The other carbon is going to be considered a substituent. All right? And I'm going to flip this thing around to make a point here. All right, we're going to call this part here our ester substituent. And this will always go out front of the name, followed by a space. So it doesn't get run in with the rest of our parent chain like we're used to here. So that ester substituent goes out front, followed by a space. All right, I'm gonna make it a different color than my normal substituents. So in this case, it's a 1-carbon ester substituent, so this would be a methyl. All right, followed by a space, and then we include our butanoate parent chain. So methyl space butanoate. Not on purpose. All right, so then let's just do let's do 2 more examples here. right, so which half of this is my parent chain, left or right? Right, because it has to contain that carbonyl carbon. So even though my parent chain is shorter here, that's perfectly allowed in the world of ester nomenclature. All right, because again, it must contain that carbonyl carbon, so the other half, these 3 carbons, are that ester substituent. The ester substituent part comes first, so this would be propyl, and then we got a space, followed by my ethanoate. All right, and then just for the sake of completeness here, let's do one more sort of tricky one. All right, let's focus on the parent chain half of this first, okay? So that would be the right-hand side here. Those 4 carbons, so a butanoate parent chain. But I have now this chloro substituent on here. And what carbon number is that chloro substituent on? Remember, carbonyl carbon must be carbon 1. So counting away, that would be a 3-chlorobutanoate There's my substituent and my parent chain. Okay, and now in this other half of our name is going to contain all that other information of that ester substituent. Okay, so these 2 carbons here, so it'll be an ethyl, but now I have another branch point off of that. I have another substituent off of that, okay? So I'm gonna have to play kind of the same game. We've seen this before with our branched alkyl groups. It's a little weird. Where am I gonna start counting? On the left or the right? What do we guess? What should be carbon 1 in this substituent? We always start labeling away from the parent chain, right? We saw this when we had our branched alkyl groups as well. The carbon that's attached to the parent chain is carbon 1 in that branched group. Same thing here. So this ester substituent would be 1-chloroethyl. All right, right, so notice how we keep these two halves of our names completely separate. There's no dichloro in there or anything like that because one's on one chunk, the other's on the other chunk, okay? And let's just make a note in our little list of notes that we have here for our ester substituent. We're going to number from that parent chain. Cool, so esters, because they have these two halves to them, are a little bit trickier than our other carboxylic acid derivatives, all right? And we're going to see something similar with amides. But actually, for our simplest amides, there's really nothing different at all, nothing complicated. So everybody take a second. Tell me the name of this 5-carbon amide real quick based on that suffix that we laid out at the beginning. So 1, 2, 3, 4, 5 carbon amide. This would just be pent and amide. All right, we use that ending amide. We got 5 carbons and they're all single bonds, so pentan amide. All right, so in that respect, there's nothing crazy going on there, all right? But this was just a primary amide. Nitrogen can have a bunch of bonds, right? It can have up to 3 bonds. So I can also have a secondary amide, where that nitrogen is not just bound to that carbonyl carbon on the one side, but an additional carbon on the other side. Okay, so first of all, what do we think is the parent chain on this molecule, the left or the right of the nitrogen? Right? Again, that carbonyl carbon has to be a part of our parent chain. So these 1, 2, 3, 4 carbons here are the parent chain in this molecule. All right, so then this thing here we're going to call our amide substituent. Okay. We do not deal with these the same way as we do esters. They don't just get listed out front, all right? They're actually dealt with much more similarly to our other substituents. Normally, though, if we had a methyl group, how would we indicate the position of that methyl group? Like if I stuck it off of this carbon over here. We would use the locin, right? We would use the carbon number, right? And that's how we indicate the position of those groups. Well, for nitrogen, when it's on the nitrogen here, I'm not going to give it a number. Instead, I'm going to indicate its position with an N. and I'm going to treat it just like a number in my name. So the name for this molecule here would be N-methyl butanamide. So this N indicates the position of the methyl group on that nitrogen. Okay, so we're going to give that methyl group a quote-unquote locant, just like we do before. It's just not going to be a carbon number. It's going to be the letter N to indicate that it's on that nitrogen in our amide. Okay, so let's just note here for amides, for our nitrogen substituents, we indicate the locant with that letter N. I mean, just say, and then build into our name like a normal substituent. All right, so then let's just do another example here. For the sake of completeness, we're going to do a tertiary amide now. I guess you don't have to be kicked up. All right, so I have these two carbons in my parent chain. All right, so my parent chain here is going to be that F-anamide. All right, but now I've got these two substituents on here, these two amide substituents. One of them's an ethyl group, and one of them's a methyl group. And I'm going to indicate their position within this molecule using N. Cool, but now I have two of them. So how am I going to arrange them in my name? Alphabetical order, right? Just like we would if there were anywhere else in the molecule. This will be N-ethyl, N-methyl ethanamide. Right? Arrange those two substituents with their locants in alphabetical order. All right, so again, the name of the chapter is carboxylic acid derivatives. And what we're going to see is a big focus of this chapter is like converting one carboxylic acid derivative into another, all right? But let's kind of start by just reviewing what we've learned thus far about how we prepare carboxylic acids. All right, so the first time in which carboxylic acids kind of came up as products of reactions were when we were talking about oxidation reactions. Right? So let's remember we had those strong oxidizers like sodium dichromate. And if we started out with a primary alcohol, importantly, it had to be not just any old alcohol, but specifically a primary alcohol. We could use these strong oxidizing agents to get a carboxylic acid. So if I start out with a 3-carbon alcohol, I'm going to get a 3-carbon carboxylic acid. All right, and remember that's because that strong oxidizer, let's just note we called this our strong oxidizer. Okay, it would not only oxidize that primary alcohol once to an aldehyde, but it would then further oxidize it again to the carboxylic acid. You can't stop at that aldehyde step, right? So for that, by that same logic, if instead of starting with a primary alcohol, we just started with an aldehyde, so we had a carbon-oxygen double bond, well, now all of a sudden we're just halfway there. So we could treat that with our same strong oxidizing agent and get that same carboxylic acid product. All right, another reaction that we had talked about was, and this was kind of oddly placed in the aldehydes and ketones chapter, but nonetheless, we talked about how if we had a nitrile, okay, we could create a carboxylic acid by just using acidic conditions and heat. All right, so everybody take a second and give me our carboxylic acid product. Make sure you are counting your carbons carefully in that nitrile. Okay. Cool, so we got one more way to prepare carboxylic acids, and it's kind of new, but it's really not all that new. And that is going to be using our Grignard reagents. Grignards, we had learned, react with aldehydes and ketones because they're good nucleophiles and they attack that electrophilic carbonyl carbon. All right, well, if we use a very special, what actually wouldn't be considered an aldehyde or ketone, but is very similar, carbon dioxide, technically not an organic molecule because there's no hydrogens in there, but nonetheless has a nice electrophilic carbonyl carbon going on, right? Carbon double bonded to not just one, but two oxygens. We can again get a Grignard reaction, all right? So if they toss in like dry ice into their Grignard reagent, all right? And what we're gonna see is our normal old nucleophilic attack of that carbonyl carbon. Okay, what's going to happen when that carbon gets attacked? Can I just leave it with that one arrow? No, right? I got to make sure not to break carbon's octet. So I'm going to kick a pair of electrons onto one of those oxygens. And just note, just based on the exact same logic that we've seen before about how Grignards react with carbonyls, now we'll have created this carboxylate ion. So then we do our last Grignard acidic workup step. Add in some hydronium. Even just do water, but they tend to use weak acid. And you'll get this carboxylic acid. One thing to kind of make special note of here, what happened to the number of carbons in this reaction? It increases by exactly one, right? You incorporate that one carbon from carbon dioxide to get your carboxylic acid. Okay, so we could just kind of summarize this. I'll leave this mechanism here. But like our R, M, G, B, R. All right, in our reagent list, we would first have that carbon dioxide and then that acidic workup. All right, and importantly, on the other side, we would get our same R group plus one additional carbon. Okay, so we can use our Grignard reagent with carbon dioxide to create a carboxylic acid as well. Okay, so here's our preparation of carboxylic acids, three of which we've sort of were introduced to previously, starting with either alcohols or aldehydes, treating them with that strong oxidizing agent to create a carboxylic acid. Or we can take our nitrile with just acid and heat to get a carboxylic acid. And then we got a new one here using our Grignard reagent. If we react a Grignard with carbon dioxide, we get a carboxylic acid that has exactly one additional carbon to it. Cool. All right, we're gonna leave it there. We'll pick up with that next time.